I'm Mercedes Jensen, and this is mine and Sam Wilson's historical presentation project for STP 308, Perspective on Math, Science, and STEM. Our presentation is on graph theory.
As Mercedes mentioned, my name is Sam Wilson, and this is our project on graph theory. So graph theory is a topic within discrete mathematics. Graph theory looks at graphs that are composed of lines and dots that, quote, represent connections between a finite set of discrete objects. And this is quoted from Discrete Mathematics with Dr. Emily Hancock. And so what we're really looking at is the connection between what two objects or a finite set of discrete objects has. So these objects could be what two people have in common, what two spaces have in common, and then that commonality is the connections that we're looking at. The graphs used in graph theory, they're not representative of functions that are used in common mathematics. So they're not going to look like our y equals mx plus b or parabolas, or even any of our more complicated structures like we see in geometry. They're going to be made up of things that we're going to talk about on the next slide. So Mercedes, here you go.
Ah, yes, thank you, Sam. So, our next slide talks about the parts of a graph in graph theory. There are two main components, which are nodes, better known as vertices, and the edges. So as you can see in our slide, the nodes are the vertices and the edges are what are connecting those vertices.
As Mercedes was saying, vertices or nodes and edges are the two main components of graph theory. However, there are other terms involved. Order is the total number of nodes or vertices. So this is the total number of finite objects we are dealing with. Size is the total number of edges. So this is the number of connections between the finite objects or nodes or vertices. The degree is the number of edges connected to one node. So it's the number of connections that are made from one object. Adjacent nodes are nodes that are connected by an edge. If two finite objects are connected together by an edge, that will be an adjacent node. Connected graphs are graphs that all of the nodes are connected to each other. That does not mean that every node has an edge to every other node, but it does mean that every node and edge is contained within one unit. A non-connected graph in graph theory would look like if we had nodes and edges over here, and then we had a few nodes and edges over here, but they're part of the same finite object set, but they're not connected together by edges. A complete graph, however, is when all of the nodes are adjacent to each other, meaning all of the nodes are connected in one way, shape, or form to all of the other nodes in that graph or finite set of objects.
Now that we have looked at used in graph theory, we're going to look at a few different representations of the graphs that you can make. So we have 6 different types of graphs here. We have social networks, economic networks, biomedical networks, information networks, web and citations, internet, and networks of neurons. As you can see, when the amount of nodes increases, the graphs can get quite complicated. So a thing you can do to help keep them looking organized and neat is to color code them, which often helps read them. So another important note to add is that these graphs can be used for many different disciplines. There is a social network example and also a biomedical network example. These have nothing to do with each other, but they can both be organized and connected to each other by graph theory. So whatever the nodes represent is being connected while keeping it organized, and even more so if you choose to color code it. So an example of a node, we're going to use social networks for this example, would be if each node is a profile and each edge is how those profiles are connected. So one of those nodes could be your profile, and every edge coming off of your profile is one of your friends on Facebook.
All right, so now that we've looked at different representations of graph theory, the big question is, who came up with this and why? So as you may have in your own brain, especially during quarantine, other people in history have also had some pretty crazy thoughts. And some of those crazy thoughts turn into math theories. This one happened to do with bridges and a little town in Prussia. So in the last slide, I had talked about a bridge in a small town in Prussia and how this turned into graph theory. This bridge and problem is specifically known as the Königsberg Bridge problem. Königsberg was a city in Prussia, which is now in Russia and was formerly in Prussia. And it's positioned along the two sides of the Pregel River with two islands in the river. The city of Königsberg constructed 7 bridges connecting the 4 land masses. So we have 4 total land masses and 7 total bridges. How did this turn into a math problem?
So as Sam said, what does this have to do with math? You might think absolutely nothing. And if you don't know much about graph theory, that's probably the right answer. But this man decided that he was going to try to cross every bridge between the 4 land masses only once. How is he going to do this? Take 30 seconds to see if you could walk over every bridge only once. Doesn't seem possible, does it? That's because it isn't.
As Mercedes mentioned in the last slide, she said this man. Who is this man behind graph theory? His name was Leonhard Euler. He lived from 1707 to 1783. He invented much of modern mathematical terminology and notation and made important discoveries in calculus, analysis, graph theory, physics, astronomy, and many other topics. Euler was the first noted person to discuss this type of mathematics. He called this concept graph theory, which is a part of discrete mathematics. Euler also invented the Euler path and Euler circuit. A Euler path is a path that visits all of the edges. So in our bridge problem, that means that he would cross every bridge. Euler paths do not focus on the nodes or vertices. However, they only focus on the edges. A Euler circuit is a path that visits all of the edges and begins and ends in the same place. For example, in a Euler circuit, if you were to start at a node labeled A, you would visit all of the edges in that graph and return to node A without doubling over any of those edges. All right, on this slide, we are looking at the timeline of mathematics, specifically from around the 1500s to just before the 1900s. So we do know quite a few people on this list. We have Da Vinci, Newton, Lovelace, and Nightingale are all on this list. And in the green box here, we can see Euler. And as I mentioned before, that falls right around the beginning of the 1700s to just about the end of it. There are mathematicians before Euler and there are mathematicians after Euler. However, that does not make his discovery any less important, especially for graph theory, because he is really the man who founded graph theory, which really led to the push in discrete mathematics.
As we saw on the previous slide with Sam, there are many people before Euler who made important discoveries. We are going to specifically talk about Newton, who was an important mathematician right before Euler. Newton conceived the method of fluxions and applied them to the quadrature of curves. A fun fact about Newton is that him and a mathematician from Germany, Mr. Leibniz, independently developed the theory of infinitesimal calculus, but both claimed that the other had stolen their work. Who really came up with it? We might never know. But between 1665 and 1666, Newton developed a new theory of light and discovered and quantified gravitation.
Slide, Mercedes talked about before Euler. In this slide, I will be talking about after Euler. After Euler came Hamilton, and no, not Hamilton like Alexander Hamilton in the Broadway play, but Hamilton the mathematician. Hamilton was a very important mathematician who contributed to graph theory after Euler. Hamilton created the Hamilton path and circuits of graph theory. A Hamilton path is a path that visits each node only one time. Remembering back to a Euler path, we only visit each edge. But in the Hamilton path, we are focused on the nodes or vertices. A Hamilton circuit is a path that begins and ends at the same node and visits every other node only once. Using a similar example to the Euler circuit, if we are finding a Hamilton circuit and we start at node A, we will go to all the other nodes and return back to node A in the end.
As previously mentioned by Sam, there is both Euler and Hamilton paths and circuits. On the left, you see a Euler path, which is focused on going through each edge only once. It does not matter how many times it goes through the nodes, because it is only focused on passing each edge once. Just like Euler when he was discovering the theory with the bridges. He wants to cross each bridge only once. It does not matter how many times he goes on the landmasses as long as each bridge is only crossed once. However, on the right, we see a Hamilton circuit where the nodes are the main focus here. Not every edge has to be crossed unless it pertains to crossing each node.
In this slide, I will be talking about relevant mathematical ideas. As noted before, we looked at different networks and plans using graphs. Specifically, we discussed the model of a social media network or graph. On this slide, to the right, you will see some data, we'll see a graph, and we'll see some charts. These are all from COVID-19. So this is happening right now. People are using COVID-19 data and combining it with graph theory to result in what you see on the slide. So that large circle with a bunch of different colors, that is a graph theory graph. The different colors represent different nodes. And of course, as we've discussed, those connections between the nodes are edges. One way you can think of this in an example of COVID-19 is we've talked about spreading the virus. So if you talk to one person, then they go talk to 2 people, 3 people, so on and so forth, it spreads rapidly. So we could say this is a tree, which would be true, and it could be displayed in a tree form. However, we could also see this displayed in a graph from graph theory.
Now that we've talked in depth about graph theory, what are its influences and its effects? Graph theory's influences are creating different problem-solving methods that we see today in schools with the use of discrete mathematics. But not only do we see it just in schools. As Sam previously mentioned, we are seeing it in real time today with the use of COVID-19 to see the connections of the virus outbreaks. We are also using graph theory to influence the recommendations for discrete mathematics, specifically systematic listings and counting, vertex edge graphs, and iteration and recursion. Now you may be thinking, graph theory doesn't have any connection to an idea or reading that we have gone over in STB 308. But in this class, we discussed education reform. Graph theory would fall under reformed education, given the discovery-based pedagogy, emphasis on logic and concepts, and the problems being contextualized.
Graph theory is seen throughout different mathematics courses. However, besides discrete mathematics, I personally hadn't come across it until last week. One example being that in CWU's Math 407 upper level math honors seminar with Dr. Boersma, we were looking at projective set. And this image was shown to us, and I realized this is a graph from graph theory. The cards from projective set being the nodes, and the connections for the p-lines being the edges.
These are our references that we have compiled from different articles, videos, and class lectures pertaining to graph theory.
That concludes Mercedes and I's presentation on graph theory and Leonard Euler. If you have any questions, please feel free to email us, and thank you for watching our presentation.